Remember what the time-varying covariate model looks at. After controlling for any systematic, like linear change, is there any occasion-to-occasion association that might explain peaks and valleys in RDV? Now, there's one little SEM trick we have to remember to make the model like MLM. Remember that in MLM, when we get the B weight for a time-varying covariate, we generally don't get one B weight for occasion 0 and another B weight for occasion 1, and so forth. Instead, we get an average fixed B weight for the time-varying correlation over all occasions. In SEM, we do that via constraining to equality. So this is a time-varying covariate model. Here we've measured negative mood at each of the 5 occasions, and the first thing to notice in the lower left is that each mood outcome is allowed to predict its concurrent pain outcome. And if you look at each of those 5 paths, it has a common label of B. Now this is how we impose a common B weight for the time-varying association across all 5 occasions. Looking back at the 5 negative mood variables, you'll see we're not imposing any fixed intercepts or anything. We're also, as you see in the box on the left, allowing all the negative mood variables to correlate with one another. Why? Well, when they're not loading on a common intercept and slope, you're not capturing the level and association of the variables in a common process. So for the model to fit well, you have to capture that association and level in a different way. So we're freely estimating the intercept of each mood variable, and this pattern of association among the negative mood variables, you will recall, is something we always did in longitudinal SEMs. We said that it was a required default assumption in multivariate. The only reason we don't have to do it when there's an intercept and slope is because we capture level and association in the higher order constructs. Okay, let's focus on the findings. So this is just like our previous growth model, except check out lines 17 to 21. Here we're allowing a fixed averaged regression relationship B1 where pain is regressed on mood at each of the occasions. And here are those extra statements to allow the negative mood terms to correlate with each other. As always, most of our factor loadings are set, so we don't care about them, but the 4 in the box at bottom represent the unstandardized B weight, forced to be the same over all occasion, looking at how well mood predicts pain. And we see that B weight is 0.476 and is significant. So yes, we have a time-varying association. We'll come back to the finding a little later on in this week's presentation. Now, we see that the pain intercept and pain slope have slightly different values than in the unconditional model, and that reflects that these are now the conditional intercept and slope after controlling for the time-varying covariate. This isn't substantively interesting, except it shows that it was good that we allowed all these negative moods to correlate with each other over time because they were all significantly correlated. We see that despite including the time-varying covariate, pain intercept and slope still have random variance to explain, and that actually makes a ton of sense because we haven't predicted the pain intercept and slope yet. We will in a minute. I've said before that the fit of these models doesn't matter a lot, but you don't want them to fit terribly. And frankly, the fit here is not good because I just really wanted to demonstrate how to do time-varying covariates. I decided not to fiddle with this model much more, but you'd probably have to if you wanted to continue with this approach. I said just a moment ago, we haven't predicted the pain intercept and slope yet. We will in just a minute. And now we're entering into a new area we haven't considered yet. We can have 2 growth models at the same time. A linear growth model for pain, a linear growth model for mood, and then we can look at how the intercepts and slopes of mood and pain are correlated. This answers a different question than, are the peaks and valleys of one variable related to the peaks and valleys of another? Instead, this asks whether the individual differences in intercept and systematic rate of change in one variable are related to the intercept and systematic rate of change in another. And when we ask this question of associations via correlations, as we're about to do, we call this the associative model.